Hi there, welcome to your physics review. Today we're looking at the conservation of momentum topic. So here we go. Just in preparation for your quiz, which actually won't be tomorrow, or because tomorrow I think is a Saturday from when I'm scheduled to do this lesson with you guys. So it'll be next week after we do the lab. So this becomes a good reference for you for later on to review right before your quiz next week. All right. The law of conservation momentum says that the total momentum of all interacting objects must remain the same. And that's the critical component here is that the momentum of all the interacting options is going to be the same. And so we've talked about that the initial momentum often was equal to our final momentum was a way of mathematically representing that statement there. So just want to keep in mind, it's going to be the same no matter what happens. Now, which type of collision is kinetic energy conserved? Now, remember, in our conversations, there were two types of collisions. There is an elastic collision, and there's also an inelastic collision. So in this question here, you're just trying to determine which one is it going to be, and which one of these collisions is the kinetic energy actually conserved. Now, kinetic energy is the energy an object or particle has due to its motion, and now coming up that later on. But when it's conserved, that's going to be in an elastic collision when it is conserved. Okay, so which means then that if we talk about and when and what kind of collision is the final kinetic energy less than the initial kinetic energy? That will be our other option, which is the inelastic. And that's because there is a portion of the energy that may be lost somewhere in that process there. Maybe lost through things like, I think it was like heat, and we talked about heat. You talked about noise and potential energy is sometimes is how it kind of gets converted in those things in those situations. In a closed system, the sum of the external forces is equal to zero. And in the closed system, the momentum is conserved. A lot of what we're talking about today is these things are in a system where they're all just inside and they're all acting in this little space. And they're acting on one another in the little space. And so it's a closed system where there aren't any external forces that are affecting it. Kinetic energy is the energy an object or particle has due to its motion. All right. So let's get into some kind of problems. Let's consider a system of two cars are traveling toward each other. Car one has a mass of 400 kilograms and a velocity of 6 kilograms. So here's car one. Car one has a mass of 400 kilograms and it has a velocity of 6 meters per second. Car two has a mass of 300 kilograms, mass 300 kilograms, and a velocity of negative 3 meters per second. What is the total momentum of the system before the cars collide? So to find the total momentum, essentially we're doing the momentum of one plus the momentum of two is going to be equal to our total momentum. And so in this case, momentum is found by mass times velocity. So our mass times velocity here, 400 times 6 is 2,400 kilograms times meters per second. And then we're going to add that to 300 times 3 is a negative 900 kilograms times meters per second. And when we combine those together, we're going to end up with 1,500 kilograms times meters per second is our total momentum in the system before the cars collide. Nothing around there. We have an even number, so it's pretty nice there. But do keep in mind that because this is a negative value here in car number two, we end up with a negative 900. And so we have 2,400 minus 900 to get us to the 1,500 value there. All right. So if this was to continue and they were to collide and crash, we know that we get just another statement here that because initial momentum is equal to final momentum, we could work out an equation and actually say that in the final after the crash, the momentum still would be equal to 1,500 kilograms times meters per second. Not asking that, but we could say that if we wanted to. A cue ball has a mass of zero point 0.8 kilograms. During a game of pool, the cue ball is struck and now has a velocity of 4 meters per second. So here's kind of our cue ball, C ball. Okay, and it has a mass of zero point 0.8 and it has a velocity of 4. When it strikes a solid ball with a mass of 0.08 kilograms, the cue ball comes to a stop. What is the new velocity of the solid ball? So that's a solid ball here. So in this situation here, what we're going to do is we're going to take the mass of the first one and the velocity of the first one, and we'll add it to the mass of the second one and the velocity of the second one. And because momentum is conserved, we're going to say it's equal to the mass of the first one, or the first one's kind of final, and the velocity of the second one. This is kind of our final, and it's our initial, plus the mass of the second one, velocity of the second one, final. So in this situation, we could kind of plug in some values. We know for our first one, we're going to make that our cue ball. We have 0.8 times the velocity of 4. And when it strikes the first ball, it doesn't say it's in the problem. I probably should have been more specific here, but the solid ball, we're going to assume is not moving. We're going to assume that it has a same mass. Well, it has the same mass as 0.8, but we're going to assume that it's stationary. The solid ball is not moving initially. And we're going to make that equal to the same cue ball, 0.8. And we know that it comes to a stop, so it's going to be 0. And then it's going to be equal to the mass of the second ball. And we want to find out its velocity when it moves as well. So a few things we could look at here, and there's not actually a lot of math that really needs to be done. Because this is an equal sign, things are going to be balanced. We notice over here we have zero point 0.8 times 0, which is 0, zero point 0.8 times 0, which is 0. So that all in a sense goes away, and we're left with zero point 0.8 as a mass times a velocity to 4 equals, on the other side, zero point 0.8 times a velocity final for the other ball. So if I divide both sides by zero point 0.8, which I certainly could do, we're left with 4 equals the final velocity of the solid ball. And then really we should say 4 meters per second. And so what's happening is we have the velocity of the first ball, in a sense, becomes the velocity of the second ball after they move on. And that's because of our momentum remaining the same on both sides of the equal sign. A bowling ball has an initial momentum of 45 kilogram meters per second and hits a stationary bowling pin. After the collision, the bowling ball leaves with a momentum of 29 kilograms times meters per second. What is the magnitude of the final momentum of the bowling pin if it has a mass of 2.3 kilograms? All right, so here's the ball. The ball is here and it has a momentum, a p-value equal to 45. There's also a bowling pin. Let's see if we can draw this here. They're kind of curved. That's a terrible bowling pin there. And we don't know what it is, but initially its momentum is 0 because it's stationary, right? It's sitting still. So our initial is going to be a total of 45 on this side. And because our momentum on the initial has to be equal to our momentum on the final, if we said that the bowling ball um, leaves with a momentum of 29, then what's left is just the momentum of the bowling pin in the second state here, right? Which is what we don't know. 29, we can call that X. I don't know. So we could really say that 45 equals 29 plus X because these two have to combine to still be equal to the initial momentum of 45. So if we said 45 minus 29, we would say that there's 16 kilograms times meters per second remaining for the momentum that the bowling pin is going to have. This mass element actually wasn't helpful at all and not needed in this situation. Because I just want to say because momentum is conserved, I need to make sure the two sides are balanced. So I do 45 minus 29 to give myself 16 kilograms times meters per second remaining. A 30-gram stainless steel ball on a track is moving at a velocity of 5 meters per second. On the same track, a 60-gram stainless ball is moving at a velocity of negative 10 meters per second. After colliding, the 30-gram ball moves at a velocity of of negative 8. Assume there's no net force in the system. What is the velocity of the 60-gram ball after the collision? So theoretically, I should turn my 30 grams into kilograms, which should mean moving the decimal point back 1, 2, 3 spots. So I end up with 0.03 kilograms, theoretically. And for the 60, should be 0.06 kilograms there. So let's take our first ball, which has a mass of, again, mass 1 times velocity 1. So we're going to say 0.03 times a velocity of 5. We're adding to our second ball and velocity 2, which has a mass of zero point 0, or I could say 0.6, right? No, no, sorry, 0.06. This is where I always mess up my little decimals. So let's do this here. 0.06 times the velocity, which is negative 10. And that's going to be equal to our final mass and velocities. And so after colliding, the 30-gram ball has a velocity of negative 8. So this becomes the 0.03 ball has a velocity of negative 8. And our 0.06 kilogram ball has a velocity we don't know. We want to find the velocity. So we'll call that velocity final. So now we're going to do some calculations with our handy dandy calculator. 0.03 times 5 is equal to 0.15 plus 0.06 times, times 10, a negative 10 is going to be equal to 0.6. So we have a negative zero point 0.6, and that's equal to 0.03 times 8, which is a negative 0.24, and that's equal plus 0.06 V. So now we need to do some calculations. I can do 0.15, sorry, 0.15 minus zero point 0.6 on this side, and I have a negative 0.45 equals a negative 0.24 plus 0.06 V. So we can add 0.2 to both sides, 24. So we're going to add 0.24 to both sides. And we end up with negative 0.21 equals 0.06 V. So now we'll divide both sides by 0.06 by 0.06, and we end up with negative 3.5 meters per second equals my velocity for the 60-gram ball. So quite a little process there. And I think the place where you're probably going to make your most likely make a mistake is just going to be in one, looking at how you convert your grams to kilograms, and then being very careful that you plug in your numbers the right way. What is interesting is if you were to say 30 for grams times 5, times 5 plus 60 times a negative 10, and set that equal to 30 times a negative 8 plus 60V, you end up with a 150 plus a negative 600 equals a negative 240 plus a 60V. And then if I do 150 minus 600, and then I do add 240, I end up over here with negative 210 equals 60V. And when I divide by 60, I end up with negative 3.5 meters per second is my velocity. So even if you were to use grams instead of converting to kilograms like you should do, you could still end up with the right solution. And the reason for that is because the grams end up in this equation canceling out in terms of the labeling part, right? So the kilograms and grams go away, and you're left with just meters per second. So you could do it that way. It's not the proper way to do it, but you do end up with the right answer. So just in case you're like, hey, I got it this way, that's why. That's because all the kilograms cancel out as you're working through the process. All right. An empty 4,600 kilogram train car is headed northbound at a velocity of 4 meters per second. So here we have a mass 1 and a velocity 1. We have 4,600 and we have velocity of 4. Ahead of the first car, an empty 2,200 gram car. Ooh, that should be changed. That should be a kilogram car. Make a note there. Mass 2, velocity 2. 2,200 kilogram car is headed northbound on the same track at 2 meters per second. The faster train bumps into the slower one and they combine into one train. What is the velocity of the two-car train? So in this case, we're going to make this equal to each other, or add them up, and we're going to make it equal to the combined masses, mass 1 and mass 2, times the final velocity that they have because they're now combined as one kind of one joint train thing. All right. So that becomes our new equation. So that our mass 1 is 4,600 and our mass 2 is 2,200 times the final velocity. So now 4,600 times 4 is equal to 18,400. And my 2,200 times 2 is equal to 4,400. And that's going to be equal to 4,600 plus 2,200, 6,800 times our final velocity. So now let's add together 18,400 plus 4,400. And we have 22,800 equals 6,800 VF. And we'll divide both sides now by 6,800. Divide by 6,800. And we end up with, I have 3.35294. It just keeps going, right? So there's my number there. I do usually want to round to the nearest tenth. So in this case here, the nearest tenth means I look next door, that's a 5, so I'm going to go up. So I'm going to say it's round to the nearest tenth be 3.4 meters per second is the nearest tenth. All right. I did make a note. I'll have to change that in my notes for later on, but that should be kilograms right there as well. So great question. This is one of the times when you would use this equation um, because we have a combined mass for our new two-car train at the end because they combine into one train. So we can combine the masses like that and just have the one common velocity for the whole system as it goes forward. So that's how that one works. All right. Here we have a 38 kilogram boy runs and jumps with a forward velocity of 2.3 meters per second into a 112 kilogram stationary boat. Stationary means its velocity is 0. What's the final velocity of the boy boat system? Another example of mass 1 times the velocity 1 plus a mass 2 times velocity 2 is going to be equal to the mass 1 plus the mass 2 times the velocity of this new system. Okay, so we have a 38 kilogram boy and a velocity of 2.3. We have a 112 kilogram boat with a velocity of 0 equals the mass of the first object, 38, plus the mass of the second object, 112, times the final velocity of the system. So 38 times 2.3 is equal to 87.4. This equals 0, so that's easy enough to deal with. And then 38 plus 112 or 150 V. So we'll do 87.4 divided by 150. And we end up with 0.582 0.6 equals velocity. And the nearest tenth here, we look at the tenth, we look next door at the eighth. So we're going to round that up and we're going to say 0.6 meters per second is our final velocity of the buoy boat system. All right, so similar to the one we did a second ago in terms of the setup there. And then we had a rounding, and so this one was just with a zero point 0.6. All right, a large silver toy car with a mass of 4.8 grams is moving to the right with a velocity of 12 centimeters per second. Notice that we're centimeters per second, not meters, or grams, not kilograms. It's not going to make a big difference because things are going to cancel out at the end anyways, but let's see what we have. The large silver car hits a smaller pink car with a mass of 2.3 grams, is moving to the right with a velocity of 5.3 centimeters per second. After the collision, the large silver toy moves to the right with a velocity of 6.4. What is the magnitude of final velocity of the small pink car? So in this case, we have the first objects plus the second object is equal to the final velocity of the object plus the final velocity of the other object. This is kind of our initial, and this is our final. It's going to be equal to each other. So now we just have a whole bunch of values to plug into this point. So I'm going to go and just keep our terms as they are, not worry about changing them around. So 48 here times 12, and this is going to be plus our pink car is 2.3, and it has a velocity of also moving to the right. They're both moving to the right, right? With 5.3. And then after they collide, 4.8 is still the mass. And so the silver car is now going 6.4. And the pink car is still 2.3, but its velocity is something we just don't know. So I have a whole bunch of values here. So we're going to do 4.8, first of all, 4.8 times 12, which is 57.6. And we're going to add that to 2.3 times 5.3, and we'll say that is 12.19, and that's equal to 4.8 times 6.4, which is 30.72 plus 2.3v. So now let's get all of our whole numbers together. 57.6 plus 12.19 equals 69.79. And we'll subtract from that 30.72 to move this one over there. So now we have 39.07 equals 2.2. We'll divide that by 2. Oh, sorry, 2 point. Look at what I did. It should be 2.3. Almost messed up there. Careful. 2.3. And we end up with a 16.986 equals our velocity. Nearest tenth in this case here, we have an here, so we're going to go up. So that means that becomes 16.9. So I'm actually going to be looking at 17. And now it's not meters per second because I didn't convert any of my units. This is actually 17 centimeters per second if I'm going to label this properly because I kept it in terms of centimeters, grams, grams throughout. So 17 centimeters per second is fine. If I wanted to turn it into meters per second, then I need to move the decimal point over. Whoops. 1, 2, 3 spots and have 0.017 meters per second there. So we could do that, but that would be a lot of work. Yeah, and maybe it's only one. Not very good at converting this, but we'll leave it like that for now. Here, that is our key thing. All right, and one final one. A ball has a mass of 0.34 kilograms and is moving to the right at 2.3. So here's our first one, 0.34, going to the right. So we usually think of that as being positive, 2.3. It's a ball of mass 0.18 that's initially at rest. So 0.18, so velocity is 0. After the collision, the 0.18 kilogram ball moved off the right with a velocity of 0.67. What's the final velocity of the 0.34 kilogram ball? Okay, so now we're looking for the velocity of this ball plus our other ball, 0.18, which now is going at 0.67. Okay, so here is the 0.34 ball, and here it is over here. We don't know its final velocity. Here's the point 0.8 ball, and here it is again with its final velocity. So essentially, we just have a lot of just little computations to do. 0.34 times 2.3, which is 0.782 plus 0 equals 0.34v plus 0.18 times 0.67, which is 0.1206. So I'm going to do 0.782 minus 0.1206. So on this side, I'm going to have 0.6614 equals 0.34. We'll divide that by 0.34, and we end up with 1.945. And the nearest tenth, I'm looking here, so we just round down, and we'll just leave it at 1.9 meters per second is the final velocity of the ball with a mass of 3.4, 0.34. And that makes sense. So that becomes our final velocity. And that really is it for this review. Hope that helps you out a little bit and you're ready to do those. Again, just a couple equations to work on and to have in mind. Make sure you're looking at the right numbers and converting things the right way and practice your rounding. That's it. Have a great day, and we'll do a quiz on this next week.